We are now going to start module 4 of chapter 5, where we will define the very important notion of adjoint of an operator. With the help of this, we will be able to define the self-adjoint and the normal operators on inner product spaces. And we will see that with the help of adjoint, we will be able to understand structures of operators much better. Eventually, towards the end of this module, we will be able to prove the Schur's theorem, which talks about the upper triangularization of a linear operator on an inner product space. V denotes an inner product space over the field F, which is either the field of real numbers or the field of complex numbers. Now, the theorem says that if V is finite dimensional over F and T from V to F is a linear functional, then there exists a unique vector V such that T of x is equal to the inner product x comma V for all V in V. In other words, every linear functional on a finite dimensional inner product space is representable by an inner product. Proof: we already know that every finite dimensional inner product space has an orthonormal basis by the Gram-Schmidt process of orthogonalization. So, let us start with an orthonormal basis B given by V1, V2, Vn. We define the vector V to be summation I is equal to 1 to n T Vi conjugate Vi. And we define a function q from V to the field F as Qx is equal to inner product x comma V. Now, a couple of observations. Q is a linear map. Well, we have already made this comment before that Q being given by this inner product where the second position is fixed by V, it is a linear map with respect to the first variable. Therefore, Q is linear, and for j equal to 1, 2 and so on up to n, Q of Vj is given by the inner product Vj comma V, but we have already defined our V, and that is given by summation I equal to 1 to n T Vi conjugate Vi. So, if you plug that in the inner product, then the expression becomes summation I is equal to 1 to n T Vi inner product Vj Vi, and that is equal to T Vj for the reason that V1, V2, Vn is an orthonormal basis for V, and therefore, inner product Vj Vi is going to be 0 for j not equal to I and equal to 1 if j is equal to I, because inner product Vj is nothing but norm of Vj square, and that is equal to 1 because B is an orthonormal basis for V. Therefore, we have proved that Q and T, these two linear functionals, they agree on the basis vectors, and therefore, they are the same, and hence Tx is equal to inner product x comma V, the same as Qx. Now, to prove uniqueness of the vector V, let there be a W in the vector space V such that T of x is equal to inner product x comma W. But then inner product x comma V is the same as inner product x comma W for every x in V. We have already seen that this implies that V must be equal to W. Let us look at this example where V is R2 with the usual inner product. Take the linear functional T of xy is equal to x minus y. Then T of E1 is 1 and T of E2 is minus 1. Therefore, by our construction of V as in the previous theorem, V is given by E1 minus E2 and that is 1 comma minus 1. And therefore, T of xy is equal to inner product xy comma 1 minus 1, and it is indeed so, because it is the usual inner product, and you can see that T of xy is x minus y, which is indeed the same as inner product xy comma 1 minus 1. Another theorem, let V be a finite dimensional inner product space over F. Let T from V to V be a linear operator on V. Then there exists a unique linear operator denoted by T star from V to V such that the following happens, that inner product Tx comma y is equal to inner product x T star y for all xy in V. So, we have to prove that such a linear operator T star exists, it satisfies this relationship and it is unique. Proof: fix a y in V and define the map Q from V to the field F given by Q of x is equal to inner product Tx comma y for all x in V. Then again it is an easy verification that Q is a linear functional. Therefore, by the previous theorem, there exists a unique V in V such that Qx is equal to, which is inner product Txy, and it is given by inner product xv for all x in V. Now define T star from V to V to be T star of y is equal to V, so that inner product Tx comma y is inner product x comma T star y. We have therefore created an operator T star which satisfies the desired property, that is inner product Txy is inner product x T star y. We have to prove two more things. One is that T star is linear and the other is that T star is unique. To prove linearity, let us start with y1, y2 in V and c1, c2 in F. Then the inner product x comma T star c1, y1 plus c2, y2 is equal to Tx comma c1, y1 plus c2, y2, and that is the same as c1 bar Tx, y1 plus c2 bar Tx, y2 by the basic property of inner product, and that is the same as c1 bar x T star y1 plus c2 bar x T star y2. And now if we push this c1 and c2 inside, then it becomes inner product x comma c1 T star y1 plus c2 T star y2. X being arbitrary, we infer that T star of C1 Y1 plus C2 Y2 is the same as C1 T star Y1 plus C2 T star Y2. Uniqueness of T star. Suppose that P from V to V is another linear operator with the property inner product Txy is equal to inner product Xpy for all xy in V. Therefore, we have that inner product Xt star y is equal to inner product Xpy for all xy V. Hence, T star y must be the same as Py for all y in V, which says that T star must be the same as P, and therefore, T star is unique. Let T from V to V be a linear operator on a finite dimensional inner product space V over F. The unique operator T star which satisfies inner product Txy is equal to inner product Xt star y is called the adjoint of the operator T. It is also true that inner product Xt Ty is the same as conjugate of inner product Ty comma x, which is the same as conjugate of inner product y T star x, which is the same as inner product T star x y. Now, what is important here is the finite dimensionality of the inner product space V. One has to remember that if V is finite dimensional, then T star exists uniquely, but if V is infinite dimensional, then T star may not exist. Such examples can be constructed. Let V be a finite dimensional inner product space with an orthonormal basis B for V. If T is a linear operator on V, then the matrix representation of T star with respect to B is the adjoint of the matrix TB. In particular, if A is an n cross n matrix over F and LA is the left multiplication operator on Fn, then LA star is the star of LA. The proof goes like this. Look at the ijth entry of the matrix T star B. So, that is given by inner product T star Vj comma Vi, which is the complex conjugate of the inner product Vi comma T star Vj, that is the conjugate of inner product Tvi comma Vj, that is the conjugate of the jith entry of the matrix Tb, and therefore, it is the ijth entry of the adjoint matrix Tb star. Let us look at this simple example. V is C2 and T Z1 Z2 is given by Z1 plus IZ2 comma Z1 minus IZ2. Take the standard basis B given by E1 E2. Then the matrix representation of T with respect to the basis B is given by this matrix 1 and I on the first row and 1 minus I in the second row. Therefore, the matrix representation of T star with respect to B is going to be the adjoint of this matrix, which is the conjugate transpose, and therefore, the matrix is 1 1 in the first row and minus I comma I in the second row. We have defined adjoint of an operator, and we have also seen that the matrix representation of the adjoint is nothing but adjoint of the matrix. So, now we will be able to use the adjoint operator, and you will see that we will prove a very important theorem about the upper triangularization of an operator on an inner product space, and that will use the adjoint. And finally, We will define self-adjoint and normal operators in subsequent modules, and we will prove very important structure theorems for such operators. In this theorem, we list down a few basic but useful properties of the adjoint. Let T1 and T2 be linear operators on an inner product space V. Let us assume that T1 star and T2 star exist. Then T1 plus T2 star is T1 star plus T2 star. C T1 star is C bar T1 star for every C in the field F. T1 T2 star is T2 star T1 star. T1 double star is T1 and I star is I, where I is the identity operator. Before we start proving, let us make this remark that here V is not necessarily a finite dimensional inner product space, and that is why we need to assume that T1 star and T2 star exist, because we have already made this comment that finite dimensionality of the inner product space is extremely important for the existence of the adjoint operator. But here we do not require finite dimensionality of the inner product space as such, we only require that the adjoints should exist. Let us prove this theorem. For the first part, let VW be vectors in V, then we have T1 plus T2 V comma W inner product is T1 VW inner product plus T2 VW inner product, and that is equal to inner product V T1 star W plus inner product V T2 star W, and that is inner product V comma T1 star W plus T2 star W, and that is equal to inner product V comma T1 star plus T2 star W. And therefore, we see that T1 star plus T2 star, which is also a linear operator on V, actually satisfies the properties of the adjoint. Therefore, by the uniqueness, we have to have T1 plus T2 whole star is T1 star plus T2 star. Similarly, we consider vectors V and W and scalar C and look at the inner product CT1 V comma W. So, that is C times inner product T1 V comma W, and that is C times inner product V comma T1 star W. If we absorb C inside, then it becomes inner product V comma C bar T1 star W, and that is equal to inner product V comma C bar T1 star of W. Again, by the same argument, CT1 star is C bar T1 star. For the third part, let VW be vectors and C scalar. We have the inner product of T1, T2, V and W is the same as T2 V comma T1 star W, and that is V comma T2 star T1 star W, and that is equal to inner product of V comma T2 star T1 star of W. Again the same argument, and it follows that T1 T2 star is T2 star T1 star. For the fourth part, if V and W are vectors, then inner product V comma T1 W is T1 star V comma W, and that is equal to V comma T1 double star W. Therefore, T1 double star is T1. And for the fifth part with the identity operator, the proof is absolutely obvious. Now, the following corollary gives the matrix analog. Let A and B be n cross n matrices over the field F, then A plus B whole star is A star plus B star, C A star is C bar A star for every C in F, A B star is B star A star, A double star is A, and I n star is I n, where I n is the n cross n identity matrix. For proving this, we can use the left multiplication operator LA and apply the above theorem, and then all the results would follow easily. Let us now prove Schur's theorem, which says that if V is a finite dimensional inner product space over F and T is a linear operator on V such that the characteristic polynomial of T splits in F, then there exists an orthonormal basis B for V such that the matrix representation of T with respect to B is upper triangular. Remember, it is extremely important that the characteristic polynomial of T splits in F, otherwise this statement is not true. Proof: let lambda in F be an eigenvalue of T. We first show that lambda bar is an eigenvalue of the adjoint operator T star. So, we start with V non-zero vector, which is an eigenvector corresponding to the eigenvalue lambda. Then for any W in V, we have the inner product of the 0 vector with W, which is 0, and that is equal to T minus lambda I of V comma W, and that is inner product of V comma T minus lambda I star of W, and that is inner product of V comma T star minus lambda by R of W. Hence, V is orthogonal to the range of the operator T star minus lambda bar I. This shows that T star minus lambda bar I is not on 2 and hence not 1 1. Therefore, kernel of T star minus lambda bar I is non-trivial, and hence any non-zero vector in kernel of T star minus lambda bar I is an eigenvector corresponding to the eigenvalue lambda bar. We now use induction on dimension of V to prove the theorem. If dimension of V is 1, then it is obviously true. Suppose that dimension of V is greater than 1. Let W be an eigenvector of T star corresponding to the eigenvalue mu in F, such that norm of W is 1. Let W denote the span of this singleton W. Then W perp is T invariant, for if X is a vector in W perp, then inner product Tx comma Cw is inner product X comma T star Cw, and that is inner product X comma C T star W, and that is inner product X comma C mu W, that is C mu bar inner product X W, and that is C mu bar 0, that is 0. The characteristic polynomial of T W perp divides the characteristic polynomial of T. Hence, it splits in the field F, and we have that dimension of W perp is dimension of V minus 1. Therefore, the induction hypothesis applies and we get an orthonormal basis B dash for W such that T W perp with respect to B dash is upper triangular. Then B given by B dash union singleton W is an orthonormal basis for V such that the matrix representation of T with respect to B is upper triangular. We must remember that adjoint of a linear operator may not exist if the inner product space is not finite dimensional. Many of the theorems that we have proved do not really require finite dimensionality of the vector space. It is enough if the adjoint exists. We should therefore be careful and verify whether the adjoint exists or not. We have already proved Schur's theorem, which talks about the upper triangular form, and the condition that we require on the operator is that the adjoint should exist and the characteristic polynomial of the operator should split in the field. In particular, if the field is the field of complex numbers, then definitely Schur's theorem holds good. Now we will see that we can extend it further and talk about diagonalizability, which is definitely much stronger than the triangular form, and for that we require some more conditions on the operator T.